Okay, welcome back, and today we are going to start chapter 4, and it's going to involve a new method of solving um, these optimization type problems, because what's going to happen is um, when we get to more and more equations with more and more unknowns, becomes very difficult to find, well, to find the corners of the feasible region. Um, First of all, we've been using a graphical approach. And when you draw these things, and you're drawing the region, it's fine if you're using two equations or three equations. You can draw the regions, but when it starts to get to um, more than three dimensionals, well, it becomes impossible to draw. So this is where we're going to revisit matrices, and we're going to use matrix algebra. We're going to use matrices to help us solve. Uh, in other words, find these corners using um, restricted row operations. Okay, so let's start. So the simplex method is what we're going to be introducing. Okay, and we're going to also go through all of the examples, definitions, theorems, properties, and things to help us do this. Okay, so the first thing we're going to do is just introduce what slack variables are and the pivot. So in this section, we're going to just um, touch upon the simplex method by just beginning to introduce some concepts and some definitions and some ideas. So the standard maximum form is when we have a linear programming problem and we want to put it into standard maximum form if we have when we have the condition. So basically, if we can have all three of these be true, then we have standard maximum form, which is what we're going to be aiming for. Okay, so one, the objective function is to be maximized. Okay, two, all variables are non-negative. Three, all remaining constraints are stated in the form of some linear combination of constants and the variables being less than or equal to b, with b being positive. Now, instead of using a, b, c, d, or x, y, z, w, we are going to replace those with just subscripts. So we're going to have x1 be one variable, x sub 2 be another one, or all the way to x sub n. So again, instead of using x, y, z, w, which can be cumbersome, we're just going to put subscripts at the end of each of these variables and just use one variable with subscripts. Okay, so to use the simplex method, we convert the constraints from inequalities to equations by adding a non-negative variable called a slack variable to each constraint. And what this variable does is it picks up the slack, in other words, when the other variables do not add up to equal the constant. Okay, so basically it picks up the slack so that it absorbs and makes it equal. Okay, so for example, if we have these two variables, we would add a slack variable 1, and we would change it from an inequality to an equality. So it's now an equation. Okay, so that way all of the points in the region that don't add up to 10, well, we'll determine this slack variable. We'll take that. So the slack variable is there to basically be the difference between what these two add up to and the constant. So we want to restate the following linear programming problem by introducing the slack variables. Okay, so here's our objective matrix right here, and here are the constraints. Okay, and we have these are also other constraints. Okay, all of the variables are non-negative, and we have these additional constraints here from the problem, let's say. So what we're going to do is we're going to add slack variables to these so we can change these inequalities to be an equal sign. So we're going to have an S1, we're going to add an S2 and an S3 to these, and then we're going to change these to equal signs. Okay, and so that's what we did. So we add these three here, but also notice that we also add the constraints that all of these three slack variables are also non-negative by what I mentioned a moment ago. Now, we rewrite all of the equations with everything to the left. This is how we set up our simplex tableau. Okay, so we take all the constraints, we take the objective equation, and we just put everything to the left except for the constant. Okay, so and also we put the constraints first. So here's the top part, and then the objective matrix goes on the bottom. And again, it's usually z is equal to these three. So we just basically move all the variables to the left, and so we get this. And then we can take this and we write the matrix in this form. So each one of these columns, this represents the column. So up here would be x1, this would be x2, x3, and then s1, s2, s3, and then this would be z. And then these would be our constants. Okay, so this would be the simplex tableau. Okay, now the last row, which is where our objective matrix is, these are what we call, these numbers here are called the indicators. Okay, we're going to talk about that later, how we use these. Except for these two. So these three and these three are called the indicators, except for this one. This corresponds to z, and this is a constant. Okay. So let's set up an initial simplex tableau. So in this example, it says a farmer has 100 acres of available land on which he wishes to plant a mixture of potatoes, corn, and cabbage. It costs $400 to produce an acre of potatoes, $160 to produce an acre of corn, and $280 to produce an acre of cabbage. Now, he has a maximum of $20,000 to spend. He makes a profit of $120 per acre of potatoes, $40 per acre of corn, and $60 per acre of cabbage. And it says how many acres of each crop should he plant to maximize his profit. Well, here's what we're going to do. We're going to do the same thing that we did before. We're going to set up our table, and we have our inequalities here, right? So we have number of acres of potatoes, of corn, and of cabbage. And we know that we only have 100 acres, or this farmer only has 100 acres, so it has to be less than or equal to 100. So we get that inequality. And then we get the cost inequality, which is this is the cost per acre for potatoes. This is the cost for corn per acre. This is the cost of cabbage per acre. And we only have $20,000. So that cost has to be less than or equal to that. And then here's the profit. And this is our objective function. Okay, so now, if we use this information, we're going to move everything to the right of the equation. So we add our slack variables, right, to each one of these. So in this case here, we're going to have two slack variables, one here and one here, okay? And then we're going to move everything to the left, which is going to be what we're going to be moving for the objective function. And then we set up our matrix. So this would be 1, 1, 1, 1, 0, 0. Okay, for the first row, that represents this one. And we have 100. And then the second one would be our cost. So this would be 10, 4, 7. So we basically divided everything by 100. Or no, we divided by everything by, what do we divide by? 40. Divide everything by 40. Okay. Yeah, 40. So we get 10, 4, 7, and then 0, 1, 0, and then 500. Okay. Now notice we divided everything by 40 before we added the slack variable, just so you know. Okay. So it's okay to simplify things and divide these. In fact, you'll see that in a lot of these examples we simplify these when we can. Okay. Um, so now we have 400, 160, 120. That becomes this row here. Okay. And then the final row, because we're moving all of these to the left, we get negative 120, negative 40, negative 60, and then of course we get 0, 0, 1 for z, and this is equal to 0. Okay, so this is our initial simplex tableau. This would be our starting point. Now, basic variables. So we're going to talk about what a basic variable is and what a basic feasible solution. So in a feasible solution, right? So we talked about last time we talked about feasible regions. So in a feasible solution, all variables must be non-negative. If there are m equations, then m variables can be non-zero. Okay, this will give a unique feasible solution to the system. So these m non-zero variables are called the basic variables, and you're going to see which ones, how we pick them out. It's very easy. And the corresponding solutions are called the basic feasible solutions. So let's use this example here, and we're going to set up the initial simplex tableau for the following problem. Okay. Now, it says a farmer has 100 acres of available land which he wishes to plant a mixture of potato, corn, and cabbage. Sound familiar? It costs him $300 to produce an acre of potatoes, $60 to produce an acre of corn, and $180 to produce an acre of cabbage. He has a maximum of $20,000 to spend, and there are taxes. Okay, there are taxes of $5, $10, and $15 per acre for each of the potatoes, corn, and cabbage, respectively. And the farmer does not want to pay more than $900 in taxes. So there's another constraint that we didn't have before. He makes a profit of $120 per acre of potatoes, $40 per acre of corn, and $60 per acre of cabbage. So guess what? Now we're going to use this information to set up our table. So we're going to write down, again, write down the inequalities, write down the objective function or the objective equation, and then we can add the slack variables. Okay, so here's the table. So we have our table. So here's potatoes, corn, and cabbage, number of acres. That has to be less than or equal to 100. The cost, right, we have 300, 60, and 180. Has to be less than or equal to 20,000. And then taxes is 5, 10, and 15, which is less than or equal to 900. Now, so we don't have to deal with these large numbers here. We can simplify this by dividing by a common divisor. Okay, one way to do that here would be to divide by 30. Oh, we could divide by 30, or we could divide by 60. Does 60 go into this? 60 does not go into this, I believe. No. So 30, I don't know if 30 does either. If we do 10, let me think. If we do 30 will work here, but what do we get over here if we do 30? We get, yeah, well, probably we'll have to do 10, see what we get. But down here we can divide by 5, definitely do that. But then here's our profit function. So, but you get the point, right? So we have this, and we can set up our tableau. Now we have to add our slack variable. So we'll have a slack variable for number of acres. So then we'll have an S1 here, we'll have an S2 here, and S3 here. Okay, and then we're going to move everything else. Everything here will already be to the left, so we can just change these to equal signs. And then these will be moved to the left because this will be equal to Z. So we're going to have minus this, minus this, minus this, plus Z is equal to 0. Okay. So now again, if the number of acres allotted in each of the 3 crops is represented by x1, x2, x3 respectively, then the constraint pertaining to the number of acres can be expressed by this equation or this inequality. Okay, where all of these are all non-negative numbers, right? So because acres can't be negative. So this constraint says that x1 plus x2 plus x3 is less than or perhaps equal to 100, right? So we're going to use s1 as a slack variable that gives this equation. Okay, why? Because then what we can do is for every value of x1, x2, x3 that does not equal 100, that's going to determine, s1 is going to determine whatever the difference is. Okay, so that it'll always equal 100. So that's why that's what the slack variable is being used for. Okay, so here S1 represents the amount of the farmer's acres that will not be used. S1 may be 0 or anything up to 100. Now, if the number of acres allotted to each of the 3 crops is represented by this, respectively, the constraint pertaining to the number of acres can be expressed as this. We're all non-negative numbers. Hold on a sec, we already did this. Why is it going over it again? Oh, maybe I didn't do it right. Okay, so it says I have two. Yeah, I think I have a double slide here. I don't know how that happened, but okay, anyway. So here it says, now if we go to the next constraint, it says the constraint containing to the production cost can be represented by this equation, right? Because it's 300 times the number of acres of potatoes, 60 times the number of acres of corn, and 180 times the number of acres of cabbage has to be less than or equal to $20,000, right? And then we could add S2 and make this into an equation, right? But if we divide both sides by 20, okay, then we get this equation, right? So remember what I said, divide by something. So in this case, we can divide by 20, and we get 15x1, x sub 1, plus 3 times x sub 2, and plus 9 times x sub 3, which is less than or equal to 1,000. Okay. Now this inequality can be then converted into an equation by adding the slack variable s2. And then we get this equation. Okay. And again, s2 represents the difference between what these variables add up to and 1,000. Now, if we had not divided by 20, then the slack variable would have represented any unused portion of the farmer's $2,000 capital. So instead, the slack variable represents 1/20th of the unused portion. Okay. Note that may be any value from 0 to 1,000. Okay. Now, the last constraint pertaining to the taxes can be expressed in this form, where we have the amount of taxes for the first the number of acres of potatoes, 10 times the number of acres used for corn, and 15 times the number of acres used for um, cabbage. Now we can also, like I said, divide by 5, and we get this equation. Okay, so again, it's where S1, S3 represents a fractional cost, or excuse me, a fractional difference. So now then the objective function for the profit, we represent this, but then we're going to move everything to the right um, of this when we set up our initial simplex tableau. Okay, now, so the linear program can be now stated in this form. We're going to maximize profit, so this means we're maximizing this equation, and it's subject to these constraints. But now we've got the slack variables involved, and now it's in a system of equations instead of a system of inequalities. And then we've got all of these non-negatives, right? So notice that they're all non-negative. That will always be the case. And so now we're going to rewrite our tableau as follows, right? So we're going to rewrite the objective function as follows. And we're going to complete our initial simplex tableau as follows here. So that means we get 1, 1, 1, 1, 0, 0, 0, 100. And so all of these pertain to the coefficients of the variables, okay? And so in this case here we have 100, 1,000, 180. Okay, so now, did we do this? Did we? Yes, we did. Okay, so here. Let me see, because I know we did talk about this. Okay, so let me just explain something here. So the non-negative variables. So what are the basic variables? Remember, the basic variables are the ones that are non-negative. So let me show you which ones are the basic variables. In this case here, S1, S2, and S3 are going to be the basic variables because they have non-negative here. So these are non-negative, and the rest of these are zeros. Okay, so if you have a column where you've got a number, and they don't necessarily have to be 1 here, but they have a non-negative, but only one non-negative number, and the rest of the uh, entries in that column are 0, then you have a basic variable. So the basic variables for this one are going to be S1, S2, and S3. And those are going to be important later on. Okay. Okay, so now solutions are read directly from the initial simplex tableau are seldom optimal. Meaning, if we go back to this, we know that since these are not basic, okay, so these are not the basic variables, these are all going to be 0. Okay, the variables here are non-basic, or they are going to be 0. Okay, which means all of these go away, and we end up with z is equal to 0, which obviously is not a optimum value. So this solution is not going to be optimum, okay? Especially when you're maximizing something, okay? So we have to find other solutions. So this is where the idea of finding the other corners are. So solutions read directly from the initial simplex tableau are seldom optimal. It is necessary to proceed to other solutions corresponding to other corners of the feasible region. To get to these other solutions, we use restricted versions of the row operations from Chapter 2 to change the tableau by using one of the non-zero entries of the uh, tableau as a pivot. Okay. The row operations are used to change all entries in that column containing the pivot to 0. Okay, except for, of course, the pivot itself. So in this chapter, by adding a multiple of one row to a multiple of another, we will never take a negative multiple of the row that's being changed. Okay, this is disastrous to the bottom row when we use the negative entries in choosing a pivot. And the reason why is because when we do that, it's going to change positive entries to negative and vice versa. And so when we're trying to use the negative values in the bottom row to choose our pivot, it's going to mess everything up. So if you get negative numbers in the rightmost column, you know you made a mistake. So always be aware those numbers should never be negative. Okay, so if we look at this example here, it says we want to pivot about the indicated 6. Okay, so we're going to use 6 as a pivot. Okay, and this is the following simplex tableau, initial simplex tableau. And then we're going to read a solution from the tableau. Okay, so what we're going to do is, since this is our pivot, and of course this is a non-negative, we've got a negative entry here, so this is going to help us choose a pivot. So they're telling us this is a pivot, so we're going to use this as our pivot, and we're going to change the rest of these to zeros using this pivot. Now, one of the things we're going to do is in class, I always change the pivot to a 1 first and then change everything to a 0. In this textbook, we change everything to a 0 first and then multiply by whatever we need to change the pivot to a 1. And we'll change all of the, so, and in the textbook, they eliminate all of the variables first, and then they multiply or divide by whatever they need to put the ones. And I mentioned this in class before. But what we're going to do is, in the simplex method, we are going to do that. We're going to follow the textbook. And the reason why they do that is it avoids having fractions and decimals as you're solving these. Okay, so you're only dealing with whole numbers. So in that case, it's less likely to make a mistake, especially when you're dealing with fractions. Okay, and then once they solve everything, then you divide through to change everything. Everything that needs to be changed to a 1 gets changed to a 1. Okay, so but anyway, let's start with this. So we're going to use the 6, and we're going to change these to zeros, right? So one thing we're going to do is we're going to multiply by negative value here, but we're going to add it to a positive multiple here. So we're never going to multiply this by a negative number. Okay, so in this case here, we're going to multiply by negative 5 here, this whole row by negative 5, and we're going to multiply this by 6. Okay, and so if we do that, we're going to get rid of this. This will go to 0, and all of these will change using our elementary row operations. So what will happen? So this is going to be negative 15, which is going to give us what? This is going to get negative 15. This is going to be 48, right? So then we get 48 minus 15 is going to give us this entry, okay? Which is going to give us, what, 33. And then if we do negative 5 times this, plus 6 times this, it gives us negative 30 and 30. This will give us our 0 here. And then here we get negative 10, and here we're going to get 24, which is going to give us a 14. And then this is going to be negative 5, which is going to give us a negative 5 here. And then the rest of these are going to stay the same because these are all zeros. And then this is going to give us a negative 300 plus a 4800, right, or 480. And then we're going to add those, and we're going to get a new column. And then we're going to do the same thing with the third row. We're going to take, in this case, it's just negative this row plus this row. So this will be negative 3 plus 3, which is 0. This will give us negative 6 and 6, which will give us 0 here. This will be negative 2 and 7, which is 5. And then negative 1 and 0, which is negative 1. And then the rest will stay the same, and this will be negative 60 plus 120, which will give us 60. Okay, and then we're going to do the same thing for the last row. Okay, and so these are the elementary row operations. Okay, so negative 5, row 1, plus 6 times row 2, and we're going to replace row 2. Negative 1 times row 1 plus row 3, and then we're going to replace row 3. And then 25 times row 1 plus 3 times row 4 will then replace row 4. Okay, and when we do that, we'll end up with this tableau. Okay, now this tableau, now if we look at this, we look at the basic variables. So what are the basic variables here? Okay, the basic variables are this one, because there's a non-zero here with zeros. This is a basic because we got a non-zero entry with zeros here. And then this one is non-zero. Okay, all the rest of these are not basic variables. So we've got x2, s2, and s3 are all the basic variables. Okay, all the rest of these variables we consider 0. Okay, so those are going to be our non-zero variables. The rest are 0. So now when we look at the bottom here and we want to solve for z, okay, well, this is not basic, so this is 0, this is 0, and this is 0. So guess what? We get 3z is equal to 1500, which gives us what? Well, z is going to equal 500. Okay, so that's going to be our profit. Okay, now, I did that by just looking at finding the basic variables and then knowing that the other non-basic variables are 0. Okay, because the basic variables are the ones where they're non-zero variables. The rest of the variables are 0. But also, to be able to read the answer directly from the bottom, we will divide our non-zero by 6 and 1/3. Okay, so we're going to divide this row by 6 to make this a 1. We're going to divide this row by 6 to make this a 1. And we're going to divide this row by 3 to make this a 1. Okay, and then from there we can ignore these because we get this here. So this is our matrix. Okay, notice that now we have fractions in here, but notice that again, where are the non-zero, or in other words, basic variables? Well, this one, and this one, and they're all ones. Okay, the rest of these are 0, are considered 0. So we know this is equal to 10, right? This is equal to 30. This is equal to 60. Okay, so if we have 10 acres, right? 10 acres of corn, and then this is our slack variable. This is the difference between S1, S2, and S3, right? Is 30. But what we really want to know is this one. So all of these are 0, right? This is just 0, but this is 0. This is going to be 0. This is going to be 0 because these are the coefficients. But remember, this variable is 0, this variable is 0, and this variable is 0. So all of these are going to go away, and we're going to end up with z is equal to 500, which is what we just came up with. Okay, and so notice here, again, that you have all of this equations, right? So that you add these, but again, the variables are 0, here, here, and here, and here, and here. Okay, so all these are 0, but then these are also going to turn out to be 0 because the variables are 0. Okay, and so again, we get z equals 500. Okay, now, this may or may not be the optimum value. Okay, so this is just another solution. Okay, so we just did it once. But now you can do this in your calculator, and here's the initial simplex tableau. And again, if you use your elementary row operations in the calculator, you do it the same way in the calculator. And you get your final answer, and you basically take your multiple of row 1/2, right? So you multiplied this by 1/2. Okay, so this is the original, this is our other example. This is not the same example here. Okay, this was a different example. This is, where is it? The very first example we did. Where is it? This one. So we're back to this example. So if we go to the calculator, we have this initial tableau, and we want to solve this and maybe use this as a pivot too here. And we want to use this we solve this one. So in this case here, they used which one? Yep. Oh, here. Yep. So we have this one here. And so they're using this as a pivot. Now, here's the thing with the calculator. Okay, so when you do this in the calculator, you have to do it not the way they do in the text, but the way I usually do it on the board. Okay, in the calculator, you have to change the pivot to a 1 first, and then use the pivot to eliminate the other rows. Okay, so in the textbook, when you do it by hand, you can do it this way by hand too, but the reason why the textbook leaves it to the end to change the pivot to a 1 is to avoid having fractions while you're doing their elementary row operations. Okay, so to avoid fractions and to just deal with whole numbers until the very end, they use the pivot to eliminate the other entries in the column, and then at the end divide by whatever you need to divide by to make that entry 1. Okay, but in the calculator, you have to change the pivot to a 1 first. Okay, so in this case here, we're going to take this, we're going to use this here to find our solution, or to find the next corner solution, or corner point. Okay, to find our next solution. So we're going to first divide by 2 or multiply by 1/2. Okay, so they're going to multiply by 1/2 row 1, and we're going to replace the matrix A. Okay, so this is our new matrix, right? So now we've got a 1, and now we're going to use this 1, our pivot, to eliminate the rest of these and make them 0. Okay, so we've changed these to a fraction. Again, as usual, you want to change these to a fraction. And then we're going to use the pivot to change these to zeros. Okay, and again, how did we change these to zeros? You remember, you take the negative of this plus this. We never take this a negative multiple of this. So it's negative row 1 plus row 2. So you'll do that in your calculator using the functions. Okay, and then you're going to take negative 2 times row 1 plus row 2. And then you're going to do 3 times row 1 plus row 3. Okay, and that's where you're going to get this matrix here. Okay, and then now you've got this pivot here, and notice that you've got this is a basic variable, this is basic, this is basic. Now of course your z is, we never use that as a basic because that's what you're trying to maximize. And so this is going to be 1 1 1. So what's going to happen here is this is going to be 0, so this is going to be 0, right? So 0 times this. These are all basic, non-basic variables. These variables here, so these are all going to be assumed to be 0. So all of these go away, and you end up with z equal to 225 as a solution. Okay, that's it. So what we're going to do now, next time, is we're going to continue on with this idea of using the simplex method, and we're going to start putting this together and start applying to maximization problems. And how do we find the actual solution to the maximization problem? So what we just did was we went through a process of using a pivot, right, and this idea of basic variables and the pivot, and using the pivot to find a solution to an initial tableau. Okay, and also the initial tableau gives us a solution, but that seldom is the optimum solution. So what do? We use a pivot to solve for another solution, to find what, basically using this to find one of the other corners of the feasible region. Okay, so next time we're going to go one step further, and we're going to say, okay, well, how do we handle this in maximization problems? Okay, now that we got the basic method down, okay, now the next step is, okay, how do we apply this to maximization problems to the end? Okay, so that's going to be next time. So again, practice these. These are not the only examples in the textbook. So practice these examples. Practice the other examples in the textbook too. And also start working on the exercises. If you get stuck, let me know. Bring those to class. If you have a question or something that you don't understand in the lecture video or in the textbook, bring those to class. We'll work through them in class. First thing at the beginning of class, we'll tackle those, and then we'll move on to practice uh, and exercises. Okay? Until then, have a great day.